So let's move on to the next talk. And the next talk will be given by Leah Clark from University of Michigan. Leah, can you hear me?
Yes.
Okay.
Can you?
Yes. Can you please share your screen when you're ready? And the title of the talk by Leah is Event by Event Correlations of Total Photon Energy and Neutron Multiplicity in Spontaneous Fission of Californium-252. So we are shifting to the topic of fission now. Leah, please start when you're ready.
Great. Well, thank you. Like you said, my name is Leah, and I'm a first-year PhD student at the University of Michigan in the Nuclear Engineering Department, and my academic advisor is Dr. Sarah Pozzi. And today I'm going to be presenting on event-by-event correlations of total photon energy and neutron multiplicity in spontaneous fission of Californium-252. So since its discovery in the late 1930s, fission has advanced many fields of science and engineering, but there are still several mysteries and other things we need to explore, such as in event-by-event analysis and fission fragment analysis. So event-by-event analysis focuses on photon and neutron multiplicities, whereas fragment analysis focuses on neutron multiplicities and photon energy. Our goal is to try and get the correlation between the two. We want to transition from event-by-event analysis to fragment analysis. So having investigated both in the past, a lot of literature focuses on multiplicities alone or energy alone, such as in this plot here, where we have photon multiplicity as a function of neutron multiplicity, but we want to find that transition between the two. And our goal is to get something with photon energy, such as in this bottom plot here, where we have the total photon energy as a function of neutron multiplicity. So the work that I'm showing is preliminary results, and it is of detected work where we try to get the work that combines and focuses and creates the correlation between those two. So for fission relevance, understanding fission can contribute to fundamental science research, and it's important because it can lead to advancements in nuclear nonproliferation capabilities and improve the accuracy of nuclear data, since it's a limiting factor for new technological developments. The experiment itself that I used the data from to find these correlations between the neutrons and photons took place in 2015. So it used a Kainu detector array holder, shown here, that was developed at the Los Alamos National Laboratory. It consisted of 54 different EJ309 detectors, of which 45 were actually used for the experiment, and they measured in 7 by 2 inch dimensions. And a Californium fission chamber was placed inside the actual detector array, and that was developed at the Oak Ridge National Lab. Some logistics about the experiment as well. The flight path included 1 meter from the detectors to the chamber, and it had a 100 KE VEE threshold. Now, since we want to study both the neutrons and the photons, we use these organic scintillators because they can simultaneously measure between the two. But because they can do that, we need to use pulse-shaped discrimination in order to discriminate between the neutrons and photons and get the actual data that we need. Excuse me. Now, I'm going to be showing the results of the three main results for both the multiplicities and the energy. So the first result we have deals with the multiplicities. So here we have a graph of the average photon multiplicity as a function of the neutron multiplicity. So what exactly this means is that for a fission event that has a neutron multiplicity of 1, 2, 3, and so on, we can expect on average to have a photon multiplicity of these numbers right here. I used a linear polynomial fit using the actual counts as weights, standard error of mean, and from the fit, we find that there is an anti-correlation between the two, meaning that an event that has more neutron multiplicity, more neutrons, we can expect on average to have lower photons. Now, looking at the actual values themselves, you notice that they're in decimal values, and that's because just because a neutron is detected doesn't mean that a photon will also always be detected. A lot of times, in fission, there is a lot of photon emission, but there's not a guarantee that every time a neutron is detected, so will that photon. So in events where there's neutron multiplicities, but a zero multiplicity for photons, that zero brings that average down. And that's why we have these in decimals. Now, focusing on energy now, we have energy as a function of neutron multiplicity. So in this graph right here, we have the average total photon light output, or energy, per event as a function of neutron multiplicity. So what exactly does that mean? That's saying that on average, in a particular event with one of these certain neutron multiplicities, we can expect the total photon light output from all of the photons in that particular event to be these values right here. Again, we have this negative correlation as shown from the linear polynomial fit, counts as weights again. And this is saying that in events where the neutron multiplicity is increasing, you see that the total photon light output or energy is decreasing. Another interesting plot that I've included is actually the light output spectra for photons as a function of the neutron multiplicity. And it's interesting because if you look at the neutron multiplicities for 1 and 2, you can barely see that blue line for the neutron multiplicity of 1 because it matches almost indistinguishable between that of photon or of neutron multiplicity 2. And we don't know why that is yet. We're going to be exploring that more, but I just thought it was interesting that you can barely see it. Maybe you can, but it's pretty hard to tell. And the last result I have deals with energy and photon multiplicity. So in this top plot here, just like the one I showed before, we have the average total photon light output per event, but this time it's as a function of the photon multiplicity. So what this is saying, again, in an event where you have a particular number of photons, you can expect on average that the total photon light output per that actual event will have these values. Again, linear polynomial fit, and you see that there is a positive correlation. And this makes sense because if you have an event where there are 5 photons, you're going to be summing up 5 different energies. And that number is going to be greater than if you're just summing up 1 energy right there. So we see that positive correlation. An interesting plot, though, is this bottom one, where we have the average photon light output as a function of photon multiplicity. And this is when the average photon light output is per photon itself. So this is saying that in different events where we have these different number of photons, on average, the actual energy or light output of those photons will be these values. And this is interesting because as you increase in photon multiplicity, you're actually decreasing in the average value of energy that you're expected to get. Now, for the expected impact, as I mentioned, our work is attempting to bridge that gap and transition between the event-by-event analysis to the fragment analysis. And it'll help with a better understanding of fundamental fission, as well as accuracy of nuclear data. And this work that I presented here, again, it was detected results, but it's going to be the basis for our correlated neutron photon emission, because we're trying to look at the emitted results as well. So for example, I showed a plot of what the detected energy as a function of photon multiplicity will be. We're trying to get here, where this is an example of emitted energy as a function of photon multiplicity. In respect to the MTV impact on myself, I just completed my first year as a PhD student and I have funding from MTV. So I have to point that out as well and say I'm very grateful for that. I'm also excited to be given these different opportunities to present and attend different conferences and workshops, such as the Symposium, as well as I presented back in March at the MTV 2020 workshop, which I think was probably the last time I was in a group of people that large since the pandemic. And it's been really great to meet other scientists and network with them and learn more about research as well. In terms of collaborations with the national labs, we collaborated with both Los Alamos, as well as Oak Ridge on this experiment itself. And we are open to collaborating with any other labs as well for future experiments we have within the fission group. So in conclusion, I've showed the results for the detected correlations for event by event and fragment analysis. We see anti-correlation between several different plots, including the photon multiplicity and neutron multiplicities, as well as the photon energy as a function of the neutron multiplicities, the photon energy per photon versus the photon multiplicity, and we see a positive correlation between the two of the photon energy per event as a function of the photon multiplicity. I also showed you a very interesting light output spectrum for the neutron multiplicities, where they show that the neutron multiplicities of 1 and 2 are pretty indistinguishable between the two, and we're still trying to investigate on why that is. So next steps. We need to unfold the results and determine the correlated neutron photon emission. Like I was saying, all of this is detected work, and we want to get it to admitted. We're going to be doing an MCMP simulation as well on the data, and we are in the progress of a publication, which will hopefully be out by the end of the year. And with that, I'd like to thank everyone for listening. I'd like to thank the consortium, as well as the NNSA and the DOE for their continued support in these research activities. So with that, thank you, and I'll take any questions you have.
Thank you, Leah, for this very nice, really interesting talk. Leah's presentation is open for questions. So please, if there are any questions from audience, I would like to start with that. And the question here, we have one question from Ramona Vogt, and the question is, will you try to be comparing to model simulations? Will you compare these results with simulations in the future? Is that part of your plan?
Yeah. So right now I'm working on the MCMP simulation as well. I didn't finish it in time to present the results for this, but we are definitely, going to be comparing the two.
Okay, so a question that I had is, so you seem to be measuring this total light output using a large array of organic stimulators. And so when you're measuring, the photon light output, one possibility one might have is maybe to design a mixed detector system, one in which comprises both organic simulators and inorganic simulators, which are superior for photon detection. And I was just wondering if something like that would make sense for a future experiment. Would that bring you an advantage or not? What do you think?
I don't see why it wouldn't. Based on what you were saying, I didn't actually do the experiment itself, but I think that would be really interesting to see if we could repeat it using those different detectors to see if we get similar results or different based off of the different detectors. I'll have to talk to my group about that.
Okay. We have another comment and question from Ramona Vogt, and the question is, so you will do the MCMP with what? What is the data that you're going to use, for the MCMP? The second comment is, you showed a couple of fission model calculations at the start, and are those models to be included in your analysis? It's just a follow-up.
So the first question was, what is the data I'm going to be using for the MCMP simulation?
Right. Yes.
So to be honest, I haven't looked too much into the MCMP simulation. I believe that we are going to be using, we're going to be simulating the detector as well with the EJ309 detectors and the Californium-252 fission source itself. I'm just working on the very basic MCMP simulation. I don't have too much experience with that yet, but I think our goal is to model, repeat the actual model of it with the 45 different detectors. And could you repeat the second question?
Yes, the question is, for the model calculations that for fission models that you showed in the start, are they going to be included in your analysis? Are you going to make simulations according to those fission models?
The fission models.
There are different fission models you talked about, and are your calculations going to compare these experiments, and the results with those different fission models?
Yeah. Yeah. Yes, I believe so. Yeah.
So, are there any other questions from Leah? For Leah?
I had one question actually. So I wanted to sort of get an idea for like what the timing resolution of the detection setup was. And if you had a larger Californium source, for example, could you still correlate all the events to a single fission, or would you have to worry about accidentals there in that case of correlating one event that's from a different fission to a different kind of fission because there's so many happening at the same time?
Okay. So based off of my understanding of the experiment itself, there wasn't, how do I put this? The issue of like distinguishing between the two was resolved, I think. I don't know specifically what would happen with a larger source of Californium if there were more fission events as well. I think we are planning on doing more experiments like this as well. So I'll definitely have to talk to my group and see if changing that size of that source will matter greatly, and how we will have to address it to distinguish between the different events.
Okay, thanks.
So I have one more question related to, again, the analysis from this instrument. So one of the known issues with working in such detector arrays is a possible scatter from detector to detector. So when you look at your light output, from multiple photons, do you take any special steps to, to identify whether the detectors, providing those signals are close to each other? Is that part of your analysis?
Yeah, so I think that was part of with the detector threshold, because only a certain number, there were like 2 thresholds actually set within the fission detector themselves, as well as the organic scintillators, where it was only the events that were above that 100 keV were detected in order to distinguish between them enough where they weren't overlapping, I guess.
So I understand that. I was thinking about the position, whether the detectors were in close proximity in space to each other, resulting in, impossible scatter from detector to detector. So do you take any steps to reject those events or not in your analysis? Or to account for them?
So personally, I did not do anything in that regard to the analysis that I did in terms of that. I think there had to have been, because I received like a huge data file, and I think before that data file was generated, there would have had to be those. I'm not entirely sure the logistics of the detector array itself, because I just learned about it through like different articles. I wasn't there, but I think I can get back to you on that for sure, about the analysis of the detector itself. Yeah.
Thank you, Leah. If there are no other questions, let's thank Leah again. I'll do my virtual